Welcome to the problem walkthrough for number 1697, checking existence of edge-length limited paths. In this session, we'll explore the problem, discuss approaches, and break down the solution step by step. Let's dive in. This problem involves working with an undirected graph that consists of n nodes numbered from 0 to n1. The structure of the graph is defined by an array called edgeList, where each entry, u, v, dis, represents an edge connecting nodes u and v with a specific distance dis. Alongside the graph, we are given an array of queries, where each query has the format p, q, limit. For each query, the goal is to determine whether there exists a path between nodes p and q such that every edge along the path has a distance strictly less than the given limit. The solution should return a Boolean array answer, where each entry corresponds to whether or not the condition holds true for the respective query. Now, let's look at a concrete example to understand how this works. In the first example, we have n equals 3 nodes and the graph is defined by the edges 0, 1, 4, 1, 2, 3, and 2, 0, 5. These edges define a triangle-like structure where each edge connects two nodes with a specific distance. For the queries, the first one is 0, 2, 5. This means we need to check if there's a path between nodes 0 and 2 where all edges have distances strictly less than 5. The second query, 0, 2, 6, asks the same question but with a higher limit of 6. For these inputs, the expected output is false, true, which we will now explain in detail. For the first query, 0, 2, 5, we need a path from node 0 to node 2 where all edge distances are strictly less than 5. Examining the graph, we see that the direct edge between nodes 2 and 0 has a distance of exactly 5, which does not satisfy the condition of being strictly less than 5. As a result, the first query evaluates to false. For the second query, 0, 2, 6, the limit is increased to 6. Here, there is a valid path from 0 to 2 through the nodes 0, 1, 2. The edge, 0, 1, has a distance of 4, and the edge, 1, 2, has a distance of 3, both of which are less than 6. This means the second query evaluates to true. In the second example, we consider a graph with n equals 5 nodes and the following edges 0, 1, 2, 1, 2, 4, 2, 3, 6, and 3, 4, 8. The queries are 0, 4, 10, 1, 3, 5, and 0, 3, 7. For the first query, 0, 4, 10, there exists a path from node 0 to node 4 that satisfies the condition, as all edges in the path 0, 1, 2, 3, 4 have distances less than 10. Thus, the result is true. For the second query, 1, 3, 5, no valid path exists where all edge distances are strictly less than 5. Therefore, the result is false. Finally, for the third query, 0, 3, 7, the path 0, 1, 2, 3 satisfies the condition, as all edges along this path have distances less than 7. Hence, the result is true. When solving this problem, several constraints and edge cases need to be considered. For example, disconnected graphs require that queries between nodes and separate components return false. Additionally, when the limit is very large, the answer may depend solely on whether the nodes are connected. For efficiency, the solution must handle cases with up to 10-5 nodes, edges, and queries. A recommended approach is to use the union-find data structure, also known as disjoint set union, with optimizations like path compression and union by rank. By sorting both the edge list and queries by distance and limit respectively, we can process the queries efficiently and achieve optimal performance for large inputs. To tackle this problem, we first considered a brute force approach. The intuition here is straightforward. For each query, we check if there exists a path between the two nodes specified in the query, ensuring that all edges on the path have weights less than the given limit. This can be implemented by running a graph traversal algorithm, like DFS or BFS, starting from the first node in the query. During traversal, we ignore any edges with weights greater than or equal to the limit. However, there's a significant drawback. For each query, we would essentially traverse the graph anew, which is computationally expensive. With m queries and a graph of n nodes, the time complexity of this approach becomes m asterisk, v plus e, where v is the number of vertices and e is the number of edges. This redundancy, where we repeatedly compute paths for each query, makes the brute force approach infeasible for large graphs or a high number of queries.
To address these limitations, we turn to an optimized approach using the union-find data structure, also known as disjoint set union.
Here, the idea is to pre-process the connectivity information so that we can reuse it across multiple queries, instead of recalculating it each time. The union-find approach offers a much more efficient solution. By pre-processing the graph and queries in a specific order, we can avoid redundant computations entirely. First, we sort the edge list by weight. Then, we pair each query with its original index and sort the queries based on their limit. As we process the queries, we use the union-find data structure to dynamically add edges to the graph in ascending weight order. For each query, we ensure that all edges with weights less than the query's limit are already included in the graph. At this point, checking whether the two nodes in the query are connected becomes a matter of determining if they belong to the same connected component, which can be done in nearly constant time per query. The overall time complexity of this approach is O, E plus M, log E, where sorting the edges in queries is the dominant factor. This method is not only faster but also avoids the redundancy of the brute force approach. It is particularly well suited for scenarios with a large number of queries, as connectivity checks are handled efficiently with no need to recompute paths repeatedly. Given the trade-offs between the two approaches, we ultimately chose the union-find method for its efficiency and scalability. This solution strikes a balance between pre-processing time and query handling efficiency, making it ideal for problems involving large graphs and multiple queries. Sorting the edges in queries allows us to align the incremental graph construction with the requirements of the queries, ensuring that all connectivity checks are handled in constant time after pre-processing. By leveraging the union-find data structure, we can efficiently manage dynamic connectivity in the graph without redundant pathfinding. Overall, this strategy provides the optimal balance for solving this problem, particularly when dealing with a high number of queries or large input sizes. In this problem, we are given a graph with weighted edges, and our task is to answer multiple queries. Each query asks whether there exists a path between two nodes, P and Q, such that all the edges on this path have weights strictly less than a given threshold, called the limit. To solve this, we can start with a simple brute force approach. First, we parse the input graph, representing it as an adjacency list where each node is connected to its neighbors along with their respective edge weights. We also parse the queries, which consist of tuples containing P, Q, and the limit. Then, for each query, we check if there is a valid path between nodes P and Q using either a depth-first search, DFS, or breadth-first search, BFS. During the traversal, we ignore any edges whose weights are greater than or equal to the limit. If we reach node Q during the traversal, we return true for that query, otherwise, we return false. While this approach works, processing each query independently can be inefficient, especially for large graphs or numerous queries. To handle multiple queries more efficiently, we can use an optimized approach that leverages the union-find data structure. The first step is to sort all the edges in ascending order based on their weights. This allows us to process edges incrementally as we evaluate queries. Next, we sort the queries themselves in ascending order of their limit values. This ensures that, as we process each query, we only consider edges with weights strictly less than the given limit. With our data prepared, we initialize a union-find data structure to manage connected components in the graph. Each node starts as its own component. Then, for each query, we add edges to the union-find structure as long as their weights are less than the query's limit. After processing the valid edges, we use the union-find structure to check if nodes P and Q belong to the same connected component. If they do, we return true, otherwise, we return false. By combining sorted edges, sorted queries, and the efficient union-find operations, we can significantly reduce redundant computations. Once we've processed all the queries, we return the results in the order they were given. The optimized approach is built on a few key insights. First, union-find operations like find and union are highly efficient when implemented with path compression and union by rank, achieving nearly constant time complexity. Second, sorting the edges in queries allows us to process edges incrementally, avoiding redundant graph traversals for each query. This reduces the complexity significantly compared to the brute force approach. Specifically, sorting the edges in queries takes O, E log E plus Q log Q, where E is the number of edges and Q is the number of queries. The union-find operations are close to O, 1, so the overall complexity of the optimized approach is O, E log E plus Q log Q. This makes the solution scalable even for large graphs and numerous queries. The choice of data structures plays a critical role in both the brute force and optimized approaches. In the brute force approach, we use an adjacency list to represent the graph, which allows efficient traversal using DFS or BFS. The space complexity for this representation is O, V plus E, where V is the number of nodes and E is the number of edges. In the optimized approach, the union-find data structure is used to dynamically manage the connected components of the graph. The space complexity here is O, V, as we maintain arrays for parent and rank information for each node. To understand the optimized approach better, let's consider an example. Suppose our graph has edges 1, 2, 5, 2, 3, 7, 1, 3, 10, and the queries are 1, 3, 6, 1, 3, 11. We'll use this input to see how the algorithm processes the queries step by step. To execute the optimized algorithm, we start by sorting the edges based on their weights. For our example, the sorted edges remain 1, 2, 5, 2, 3, 7, 1, 3, 10. Next, we sort the queries by their limit values, resulting in 1, 3, 6, 1, 3, 11. For the first query, we add edges to the union-find structure with weights less than 6. This means we only add the edge 1, 2, 5. At this stage, nodes 1 and 3 are not connected, so the result for this query is false. For the second query, we add edges with weights less than 11. This includes the edges 2, 3, 7, and 1, 3, 10. Now, nodes 1 and 3 are part of the same connected component, so the result for this query is true. The final result for all queries is false, true, demonstrating how the algorithm efficiently processes the input while avoiding redundant computations. To solve the problem, we start by defining a helper class called UnionFind, which is essential for efficiently handling connectivity checks. The UnionFind class uses two main data structures, a parent list to track the leader or root of each element, and a rank list to manage the depth of trees. In the constructor, we initialize the parent list so that each element is its own parent, and the rank list is set to 0 for all elements. The find method implements path compression, which helps flatten the structure of the tree whenever we traverse it. This ensures that future lookups are faster. The union method merges two sets by attaching the smaller tree to the root of the larger tree, based on their ranks. If the ranks are equal, one tree becomes the root and its rank increases by 1. This keeps the tree as flat as possible. Next, we define the main function, distance-limited paths exist, within the solution class. Here, we first sort the edge list by their weights. Sorting the edges beforehand ensures that we process them in the correct order for the union find operations that follow. Now, we prepare the queries by adding an index to each one so we can store the results in the correct order. Each query is represented as a tuple containing the nodes, the distance limit, and the original query index. These queries are sorted based on the distance limit, which ensures that we only consider edges with weights less than the current limit during processing. We then initialize the union find structure and a result list to store the answers for each query. Using a variable edge_index, we iterate through the queries. For each query, we process all edges with weights less than the current query's limit, uniting the nodes connected by those edges. After processing the relevant edges, we check if the two nodes in the query belong to the same connected component using the find method. If they do, we mark the result for that query as true. Finally, the result list, which contains the answers in the original query order, is returned. This approach ensures efficiency by leveraging the sorted order of both edges in queries to minimize redundant operations. Here, we begin by defining a union find class, which is essential for solving this problem efficiently. The union find, or disjoint set union, DSU, structure, helps us group elements into sets and perform operations like finding the representative of a set or merging two sets. We initialize two arrays, parent, which keeps track of the parent of each node, and rank, which helps optimize the union operation by keeping the tree shallow. The constructor initializes these arrays so that each node is its own parent, and all ranks are set to 0. The find method implements path compression, ensuring that nodes directly point to their root, which speeds up future operations. Finally, the union method merges two sets, and it uses the rank array to attach the smaller tree under the larger tree, improving efficiency further.
In the union method, if the roots of the two nodes are different, we compare their ranks.
If one root has a higher rank, it becomes the parent of the other. If their ranks are equal, we arbitrarily choose one root to be the parent and increment its rank. This ensures that the tree height remains minimal, which is crucial for efficient operations. Moving on to the solution class, we implement the distance limited paths exist method. Here, we start by sorting the edge list based on edge weights. This is important because we want to process edges in increasing order of their weights when determining connectivity. Next, we prepare the queries with index array, which includes the original queries along with their indices. This allows us to maintain the order of results corresponding to the input queries. We then sort the queries by their distance limits so that we can evaluate them sequentially while processing the edges. Finally, we iterate through the sorted queries. For each query, we extract the nodes P and Q, the distance limit, and the original index of the query. While there are edges remaining with weights less than the current query's limit, we use the union operation to connect the nodes of those edges in our union find structure. This ensures that all relevant edges are processed before checking the connectivity for the current query. After processing the edges, we use the find method to check if nodes P and Q belong to the same connected component. If they do, it means there exists a path between them that satisfies the distance limit, so we set the result for this query to true. Otherwise, it's set to false. Once all queries are processed, the result array is returned, providing the answers in the original order of the queries. To solve the problem, we start with the first example. Here, we have 4 nodes, and the edges between them are provided along with their respective weights. Our goal is to determine whether the specified queries about connectivity under certain weight limits are satisfied. The first step is to sort the edge list by weight. This gives us the edges in ascending order of their weights, making it easier to process them incrementally. Similarly, we sort the queries by their weight limits, while maintaining their original indices for the final result. Next, we initialize a union find structure to help us manage connected components efficiently. Initially, each node is its own parent, and the rank array is set to 0. The result array is also initialized to false for all queries. Now, processing the first query, we include edges with weights less than the limit. After adding the edge between nodes 2 and 3, we perform a union operation, updating the parent structure. Checking the connectivity between nodes 0 and 2 reveals they are not connected, so the result for this query remains false. Next, for the second query, we include edges with weights less than the limit of 4, adding edges between nodes 1 and 2, and subsequently between nodes 1 and 3. These union operations connect nodes 1 and 3, satisfying this query. The result is updated to reflect this. Finally, for the third query, we include all remaining edges under the weight limit, connecting the remaining nodes. Checking connectivity between nodes 0 and 3 confirms they are connected, and the result is updated accordingly. After completing the first example, the final result for its queries is true, true, false. Now, moving to the second example, we work with 5 nodes and an edge list that contains only 2 edges, highlighting scenarios where not all nodes are connected. Again, we start by sorting the edge list by weight, ensuring edges are processed in ascending order. We also sort the queries by their weight limits, appending indices for the final result. The union find structure is initialized similarly to the previous example, with each node representing its own component. The result array is set to false for both queries initially. Processing the first query, we include all edges under the weight limit of 5. This allows us to union nodes 0 and 1, and separately nodes 3 and 4, forming 2 disconnected components. Checking connectivity between nodes 0 and 4 confirms they are not connected, leaving the result unchanged. For the second query, no additional edges meet the weight limit, so no further unions are performed. Checking connectivity between nodes 1 and 3 indicates they remain disconnected as well. The final result for this example is false, false, showing that the queries are not satisfied due to the disconnected nature of the graph. In the third example, we examine a scenario where all nodes are interconnected. With 3 nodes and the given edges, we aim to answer the queries efficiently. As before, we begin by sorting the edge list in queries. The edges are arranged in ascending order of weight, and the queries are sorted by their weight limits with indices for the result.
The union find structure is initialized with each node as its own parent and all ranks set to 0. The result array is initialized to false for both queries. For the first query, we include edges under the weight limit of 2, adding the edge between nodes 0 and 1.
A union operation connects these nodes, and checking their connectivity confirms they are connected, updating the result. For the second query, we include all edges under the weight limit of 4, adding the edges between nodes 1 and 2, and subsequently between nodes 0 and 2. These union operations connect all nodes into a single component. Checking connectivity between nodes 0 and 2 confirms they are connected, and the result is updated. The final result for this example is true, true, demonstrating that all queries are satisfied due to the fully connected graph. In analyzing the time complexity of this problem, we start with the sorting operations. First, the edge list needs to be sorted by edge weight. If the graph contains m edges, the sorting process has a complexity of O, m asterisk log m, due to the nature of comparison-based sorting algorithms. Similarly, the queries list, which contains k queries, also needs to be sorted based on their limit values. This sorting takes O, k asterisk log, k, time. These two sorting steps lay the foundation for efficiently processing the edges in queries in subsequent steps. Now, let's focus on the union find operations required for edge processing. For each query, we add edges to the union find data structure where the edge weights are smaller than the current query's limit. By using an edge underscore index pointer, we traverse the edge list in a single pass, making this step O, m, in total. Union find's union and find operations are very efficient, with an amortized time complexity of O, alpha, n, where alpha, n, is the inverse Ackermann function, which grows extremely slowly and is almost constant for practical purposes. Additionally, for each of the k queries, we perform connectivity checks using the find operation. Since each find operation has a complexity of O, alpha, n, processing all queries takes O, k asterisk alpha, n. Combining these results gives us a total time complexity of O, m asterisk log, m, plus k asterisk log, k, for sorting, and O, m plus k asterisk alpha, n, for edge and query processing. When we combine all the components, the overall time complexity is expressed as O, m asterisk log, m, plus k asterisk log, k, plus m plus k asterisk alpha, n. However, for large inputs, the sorting terms dominate, so the complexity simplifies to O, m asterisk log, m, plus k asterisk log, k. Next, let's analyze the space complexity. Starting with the union find data structure, it uses two arrays, the parent array to store the parent of each node and the rank array to store the rank of each node. Both of these arrays require O, n, space, where n is the number of nodes. For the queries, we modify the queries list to include the original index of each query for output alignment. However, this does not increase the asymptotic space complexity, as the size of the list remains proportional to the number of queries, contributing O, k, space. Next, we consider the space used for storing the graph edges. The edge list requires O, m, space, where m represents the number of edges in the graph. Additionally, the result array, which stores the output for each query, requires O, k, space, as it contains one entry for each query. When we sum up these components, the total space complexity comes out to be O, n plus m plus k, which accounts for the space used by the union find structure, the query storage, the edge storage, and the result array. To put this into perspective, let's compare the current optimized approach with a brute force method. A naive solution would involve directly checking all paths between nodes for every query, which could result in a time complexity of O, k asterisk n squared, in the worst case. This happens because we would need to compute all pairs' shortest paths for each query, making it infeasible for large inputs. In contrast, the optimized approach leverages sorting and union find to efficiently check connectivity. This reduces the time complexity to O, m asterisk log, m, plus k asterisk log, k, which is significantly faster and scales well with larger graphs and query sets. Finally, let's examine the best, worst, and average case scenarios for this solution. In the best case, if all queries have very high limit values, all edges are processed only once, and union find operations are minimal. Here, the time complexity is dominated by sorting, which is O, m asterisk log, m, plus k asterisk log, k. In the worst case, where all edges need to be processed for every query, the time complexity remains the same due to the efficiency of union find operations. On average, the complexity is also similar to the worst case since sorting dominates the overall runtime. Mathematically, sorting bounds the complexity, while union find ensures efficient connectivity checks with O, alpha, n, per operation. The space usage remains linear, at O, n plus m plus k, due to the storage requirements of nodes, edges, and queries. In this section, we'll highlight some common mistakes to avoid when solving this problem. First, many overlook the edge weight constraints, which require that all edges along a path have weights less than the given limit. Failing to enforce this condition can lead to incorrect path validation, so it's critical to filter edges based on weight before proceeding.
Another frequent issue is inefficient path exploration.
Using naive DFS or BFS for every query can result in time limit exceeded errors, particularly for dense graphs. Instead, optimize your approach with union find or pre-computations to minimize redundant work. Sorting edges or queries by weight or limit is another essential step that many skip, leading to unnecessary computations. Mismanaging union find operations is also a common pitfall. Using unoptimized implementations without path compression or union by rank can drastically slow down your solution. Finally, don't forget to account for edge cases, such as disconnected graphs, queries where the source and destination nodes are the same, or limits smaller than the smallest edge weight. These scenarios often trip up solutions that don't handle them explicitly. Now let's discuss some insights that are particularly relevant for interviews. Union find is a foundational data structure for this problem, so make sure you not only use it effectively but also understand optimizations like path compression and union by rank. These techniques are often a key discussion point with interviewers. Sorting is another critical element in weighted graph problems, so be prepared to articulate why sorting edges or queries is a crucial step in your approach. Pre-processing is an important strategy to improve query efficiency. For example, processing edges upfront might increase pre-processing time, but it can significantly reduce the complexity of individual queries. Be ready to explain the trade-offs, such as how a union find-based approach might involve higher pre-processing costs but ensures near-constant time queries thereafter. Lastly, interviewers often expect you to discuss edge cases. Highlight how your solution accounts for scenarios like disconnected graphs or unusual query conditions, as this demonstrates thoroughness and attention to detail. Let's explore related problems and alternative approaches. Some similar problems you might encounter include LeetCode 743, network delay time, which involves finding the shortest path in a weighted graph, and LeetCode 684, redundant connection, which also uses union find to detect cycles. Others include LeetCode 1976, number of ways to arrive at destination, and LeetCode 1631, path with minimum effort, both of which involve graph traversal under specific constraints. As for alternative approaches, one option is using DFS or BFS to search for paths that satisfy the query conditions. This is straightforward to implement but becomes inefficient for large graphs or multiple queries, with a time complexity scaling poorly to O, Q asterisk, n plus E. A more efficient alternative is Kruskal's algorithm combined with union find. By sorting edges by weight and processing queries in ascending order of their limits, you can maintain connectivity information dynamically. This method is highly efficient, with pre-processing taking O, E asterisk log, E, and each query being nearly constant time. Finally, another approach worth considering is the Floyd-Warshall algorithm. This method pre-computes all pairs' shortest paths using dynamic programming. While it's particularly effective for dense graphs where every node is connected to many others, the pre-processing complexity of O, n cubed, makes it impractical for larger graphs. This trade-off highlights the importance of tailoring your approach to the specific constraints of the problem. For instance, if the graph is small or dense and you need to handle numerous queries, Floyd-Warshall may be a viable option. However, for sparse graphs or scenarios where pre-processing time is critical, union find-based methods would likely be more suitable. Great job! To wrap up, we reviewed the problem, explored the optimal solution using graph and union find techniques, and discussed the key takeaways. Keep practicing and applying these concepts to similar problems. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem.
If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!